Okay, hello everybody to this week's ISGC seminar. Today's speaker is Jutta Kunz. She did her PhD and later her habilitation at the Justus Liebig University Gießen in 1982 and 1989 respectively. And she is, or better was, since 1993 a professor at the University of Oldenburg. And currently she's also their professor emeritus and still continues to work. Jutta, thank you very much for agreeing to give this talk. And the stage is yours.
Thank you very much, Tom. It's my pleasure to give a talk here. And I will be talking about some subject that has been spoken about in the seminar, but it's kind of a popular subject, so one shouldn't wonder about that. But 2 weeks ago, we had a very nice talk by Jose, so I'm trying to be very brief on that part and focus a bit more on the other parts. So I'll be talking about compact objects and Einstein-scalar-Gauss-Bonnet gravity. And the outline is that I would first and mainly concentrate on the black holes and there discuss a few things about the different types of scalarization of black holes. Then I decided not to talk about neutron stars, where you can do the same again, but to go to these exotic compact objects, the ECOs. And I will discuss some wormhole solutions and some particle-like solutions. So this is the outline, and let's just start with some brief introduction. We, in our field, and it's a very, very exciting field currently, and it's going to be so in the future, because we have all these data now from observations. We have and are getting more data from the gravity collaboration and the observations of this gravity instrument in Chile, looking at the black holes in the centers of galaxies and in particular at our ZA star. So we have very, very precise numbers by now of, let's say, the mass and other quantities of this compact object at the center of our galaxy. And we have the nice pictures from the Event Horizon telescope, and we're looking forward to the next stage and the developments of getting more precise data from them, which are in the planning phase. And then, of course, we have the gravitational waves. And there we have so many data by now. And these data are going to increase a lot with all these new upcoming telescopes and then also different frequency ranges. So we are really in an absolutely exciting time for this type of research we're doing. Now, with all this data, we can certainly exclude a lot of gravity theories and constrain some. But yeah, some have very, very weak constraints only so far. And most constraints are then coming from the strong gravity regime from, yeah, the solar system. We know things very well, and no theory is going to survive that does not reproduce the solar system. But in the strong gravity regime, we have all these new observations and coming up observations, which are going to help us to constrain those theories and maybe rule them out. Here we have just a bunch of theories in the middle. Yeah, just yeah, what is modified gravity going beyond general relativity somehow? But there are many, many directions one can go. And today I would just go in this direction up here, introduce some extra degree of freedom, and this should be a scalar, and then go to this set of theories called Horndeski theories, and this is still a very wide set of theories, and there I will focus on the Einstein-scalar-Gauss-Bonnet theories. And this is how these theories look like. here we have the action, and here this is just the Einstein-Hilbert term. Then we have the free scalar field part, and then we have coupling constant, which I mostly call alpha, a coupling function of that scalar field, and it's coupled to an invariant, the Gauss-Bonnet invariant, and this is how this invariant looks like. It's a quadratic and curvature invariant, and these days this type of theory is mostly considered from an effective field theory point of view. So you may say you make an expansion and derivatives of the metric, and then these terms is what you get, of course, not necessarily with those coefficients. And yeah, you get some other term, but this is a really nice combination. And it's so nice, not only because all these terms you get from such an expansion, but yeah, it's also seen from string theory, where something like this arises, and from the string theory point of view, it was the first investigations that were made in this type of theory. And then when you use it, you obtain, since it's a Horndeski theory, you obtain second order field equations, and yeah, you know how to handle these, because yeah, it's like in GR. And there are no ghosts, so it's a pretty nice setting in which you're doing investigations, and yeah, try to constrain this coupling constant for a given coupling function. Now, this is how the field equations look like, and you see what we have here is the energy momentum tensor, stress energy tensor of the scalar field. It's just the usual one. But then we get this additional piece here. This is coming from the Gauss-Bonnet term. And so in total, we have some effective energy momentum tensor. And it's this effective energy momentum tensor that is giving us all these interesting new aspects. And the scalar equation just looks like some Klein-Gordon equation. And here we have a source term also coming from this coupling. Now it's really crucial that we have this additional piece here, that we have this effective stress energy tensor, because it allows us, without introducing any exotic matter, anything very strange, that we can violate energy conditions. And it allows for black holes with hair. So no hair theorems don't hold anymore. And yeah, we can have all kinds of funny solutions, like wormhole solutions, which don't need any exotic matter, or particle-like solutions. Interesting new stuff arises which we don't have in general relativity. And the coupling function is also very crucial, because the choice of coupling function tells us what type of black hole solutions are possible. And in particular, it tells us whether the black hole solutions of general relativity remain solutions, and we have in addition scalarized solutions, or whether we only have scalarized solutions and the solutions of general relativity no longer satisfy the equations of motion. And yeah, of course, we can do perturbation theory in this type of theory. And this is what Jose spoke about nicely 2 weeks ago. So I will only very briefly discuss this aspect. So let's now look at the various types and start with, let's say, the string-motivated coupling function, the dilatonic scalarization, as we like to call it. So in this case, we have this exponential coupling, and gamma, yeah, one can take as a free parameter. However, in string theory, it would be 1. And most of the calculations have been done with gamma equal to 1. Then the scalar equation is what we have to look at. And then we see that, yeah, here this derivative of the function with respect to the scalar occurs. And of course, with such an exponential, this is not going to vanish. And also not when phi, the scalar field itself, vanishes. But for a GR solution, we would need a vanishing scalar field. So now we always have a source term. So we always are going to have black holes with a scalar here and no GR black holes. They may just occur in the limit, yeah, no coupling constant, we just switch on. We start from GR. And then we might approach them. And this is what we see here. You see, this is from the very old paper from the 90s from Jutta and the group, her group at the time. And you see the radius of the horizon scaled versus the mass of the black hole scaled. And this solid curve, this is the set of scalarized black holes. And for small masses, we just stop. The solutions don't continue. We have, and this was already explained by Jose, we get in the expansion, such as square root. And yeah, if we would want to continue in this direction, then the scalar field would become complex. So no way, we don't want that. So we have to stop here. So we have a minimal mass. And this is kind of funny to have black holes with a minimal mass. So we wouldn't have this type of black hole, a static, spherically symmetric black hole, kind of the analogon to Schwarzschild. Yeah, in this theory. And I haven't seen anybody do the calculations so far, I must say, but what I would love to see is a calculation that does just the full collapse and start with a mass range so that you would end up kind of, if there were a compact object in this area where we don't have these static or stationary black holes, because for the rotating solution, that's no different. What's going to happen? I mean, so far I have seen only speculations like, okay, there might be something like a black hole, but it could be dynamical. So something tiny pen, a tiny pen solution, but yeah, it's really something I'm interested in to see. Yeah, coming back, we see as we go to large masses, we approach the Schwarzschild black holes. And when we add rotation, then we have here plotted the area of the horizon scaled versus the angular momentum scaled. And then we see right here, these are the static black holes. And we see for very large masses, we just approach this limit, the GR limit, for a given coupling constant. And then this is the set of Kerr solutions, which is the boundary. And down here, we have this boundary where the solutions just stop to exist. We would get an imaginary scalar field. And yeah, so this domain of existence is, of course, then a real domain and not just a line that we have here in this theory. And you see, and Jose pointed out also, we can go in this type of theory a little beyond the Kerr bound, but not much, just a little beyond the one. And since we had this question, I just thought I'd put in the slide. The question was on the entropy, and you see the entropy of these black holes is larger than the entropy of the pure black holes. Then, of course, how about observations? Yeah, the shadow is something one is interested in, and going back to the area, you think, you might have some effect, and you might possibly see some deviation from a core black hole with the same masses, angular momenta or so. But no, you basically see nothing. In this theory, they are very, very close. So no hope to get a bound from here. However, from gravitational waves, yes, there are bounds. And these bounds, Jose discussed already bounds last time, and he was discussing the quasi-normal modes. And this is what I just put up again. And you see here the real frequency and here the imaginary one, and the dependence on the coupling constant. This is for a relatively small angular momentum. And then you can see while you start here from the per solution from general relativity, alpha 0, you get deviations as the parameter, the alpha, the Gauss-Bonnet coupling is increased, and this is for a larger coupling. So in principle, if one would be able to obtain the quasi-normal mode spectrum now already from the gravitational wave observations, then one might get some bounds, but currently this is not yet accurate enough. One is expecting this for the next generation, 3 G, as it's called, third generation. Then one should have sufficient accuracy to really discern the spectrum of the quasi-normal modes of the ring down of the final object, and then extract something to constrain the theory. However, there are already now constraints coming from gravitational waves, and this is a very nice, interesting paper from the Potsdam group, and they calculated the waveforms in Einstein-scalar-Gauss-Bonnet, so with this exponential coupling. And so here you see the all phases, the in-spiral, the merger, and only the ring down they took then from some other paper. We had not yet finished our calculations, so they took some other theory. But what you see here, when you start at a certain time, and now you evolve, and red means you evolve in general relativity, and here it's just now continuing. And then you have the merger and the ring down. In general relativity, the time is longest. As you increase this coupling constant, the alpha, they renamed it, then you see first here the blue curves, and then the black ones for quite large value of the coupling constant. And then you see it moves to shorter times. And so from these calculations, one can already put then some new bound on the coupling constant. And they now have, as far as I know, the best bound on alpha in this Einstein-scalar-Gauss-Bonnet theory. Just because, when you have this theory, you have an extra degree of freedom. There's the scalar field. So you have more channels. And in here you saw and José explained nicely that we have, for a given multipole, 3 channels, the polar and the axial, which you have in general relativity also, but now the scalar is mixing in. But we can also have this scalar channel or scalar lit channel because they are mixing in. And you don't start at L equal to 2 because it's a scalar field, so you can have dipole radiation, and this is what you see here. So it's the dipole radiation that is emitted during this inspiral phase that shortens the inspiral phase, and you can obtain already some nice bones. So let's now look at another type of coupling function, the spontaneous scalarization coupling function. And now we take some even coupling function. And why do we want this? Now, let's look again at the Klein-Gordon-type equation here. Now we want to have the black holes of general relativity to remain solutions of the field equations. This means we need solutions where the scalar field vanishes. And so if we put the scalar field to 0, then we don't want a source term. Then this should just not give us anything. So the derivative should vanish. However, the second derivative we want to be finite, positive finite. Okay. I mean, otherwise we would have to change the sign of the coupling constant, and let's just fix it. So now, in that case, we certainly have the Schwarzschild solution and the Kerr solution as solutions of the field equations. However, we can get additional scalarized solutions. And how come? Now, the mechanism is just analogous as it's been found decades ago for neutron stars by Damour and Esposito-Fares. And it's kind of funny that after decades, at the same time, 3 groups discovered this. Now for neutron stars, this what we call spontaneous scalarization. This arises because of the matter that is present in this very compact neutron star. And we say it's matter-induced spontaneous scalarization. However, we don't have any matter when we have black holes, right? So it doesn't work there. And then at some point, to a number of people on this globe, it occurred, what black holes have is curvature. So why don't we try to have curvature-induced scalarized black holes? And curvature, you get the Kretschmann scalar is finite for Schwarzschild or Kerr, as we all know. And so having here this Gauss-Bonnet piece, which has Kretschmann as one of its sub-pieces, this gives us something finite. Even though the Ricci scalar vanishes, the Ricci tensor vanishes, here this piece gives us something from the Kretschmann. And here you see for Schwarzschild how it looks like. So we have a passive constant, which depends on the mass and the radius. So it's positive. No, maybe I shouldn't say constant, but function, because it really depends on the radius and increases as we go towards the horizon. And now when we compare our Klein-Gordon equation-like equation with the real Klein-Gordon equation, then we see this is something like an effective mass squared piece times scalar field if these conditions are proper, and maybe some higher order terms depending on what we have. So in any case, we get something that is an effective mass, and this effective mass, this becomes negative because here we have a positive piece from the Gauss-Bonnet term, and then when we take the coupling constant positive, as we of course first do, then it's negative. So what we can get, if this is sufficiently big, if we are there where we have high curvature, so close to the black hole, let's say, we get an instability, a tachyonic instability, and scalarization arises just analogous to the case of neutron stars, where it's this matter, the very compact matter that induces then this instability. And here, this is from a paper by Daniela and her group. So here, what you see is then the static, or the sum of the static black holes, this dashed red curve, this is what we call the fundamental solution. And then here you have these green and blue, and then there will be more and more and smaller solutions, which correspond to radial excitations. And interestingly, the entropy is larger for the scalarized solution than for the Schwarzschild solution. So, yeah, that indicates that one would have stability. They have constructed the solutions with this neutron star inspired coupling function. And when one makes an analysis of this type of solutions and looks at the modes, which also was discussed before, then the low modes, which we analyzed, they are stable. So here, this is then for the simplest coupling function one can choose. And actually, for that coupling function, also the fundamental solution is unstable. So this is, looks like a better coupling function than the simplest one can take. Concerning stability, I would like to make a remark. Namely, there has been a paper by Minamizuchi and Tsumukoyama, and they have investigated stability or instability of these static spherically symmetric black holes by going to a very high L, and they found some what they call gradient instability. But whenever you have an instability, of course, it matters how unstable the solution is. And we don't have any timescales from their calculations. So it's not clear, are these instabilities on relevant astrophysical scales or on huge timescales? So could the black holes exist? When this type of theory is used to calculate any collisions, one doesn't notice any instabilities. So it could be very large timescales, and so it might not be so relevant. But I think, I haven't seen it, but it's something one should, if it's not been done, investigate really. What are the timescales of those instabilities? Are they relevant? But what we observed is showing very short timescales for instabilities, and something very funny because we added also another piece here that was suggested by the group in Nottingham. and investigated by them. And they also showed when you take such a theory where you also couple with the same coupling function phi squared by 2 to that Ritchie scalar with a new coupling constant, then you have the black holes, the static spherically symmetric black holes, and they are really stable. However, when one looks at these, one finds they are unstable with respect to quadrupole deformations or higher deformations like hexadecapole deformations. So one has these deformed black holes arising in this type of theory. Yeah, it's something funny, I think, that this occurs. But let's forget about this additional coupling again and come back to just the normal coupling and look at what happens when we rotate those solutions with the curvature-induced spontaneous scalarization. And we now have the Kerr background, and the Kerr should get some instability, some tachyonic instability. But for Kerr, we have the spin, and the spin enters here in the Gauss-Bonnet invariant, and it enters with different signs. So, yeah, different things may happen. If we just keep the coupling constant positive, this alpha positive, then what is going to happen is, yeah, because these negative pieces arise, the domain of existence is going to shrink. However, it could be that if these negative terms dominate, that, yeah, a new type of spontaneously scalarized solutions arise that exist only at large spin. And this is indeed what happens. And in that case, one talks about spin-induced scalarization. And here you have the two with this coupling function that was the coupling function of Daniela and her group, neutron star inspired, and had the, at least for low multipoles, stable solutions. And yeah, these calculations have been done by the Avero group, and you see indeed here we have the positive coupling, so the domain of existence shrinks as we go to large angular momenta. But on the other hand here, we now get also spin-induced rotating black holes, and yeah, they start at this J equal to 0.5, and then yeah, you have this family of solutions. And in this case, when you look at here, you think, okay, here we have really a huge change in the radius of the black hole for a given scaled angular momentum. So it should be possible to see something for the shadow, unless, or unlike this previous case we discussed. And indeed, here you would be able to see a big difference for the same angular momentum, same mass for a black hole. What we would need in order to get some bound on the coupling would, of course, be a measurement of the spin. But yeah, these spins of the black holes are not well determined. So currently, even though there would be an effect that one can see, well, one cannot conclude on that. So the other coupling function also has something interesting, namely, I told that all the solutions are unstable also the fundamental solution is unstable. But now when we rotate, it's not that clear, hasn't been yet looked at. The domain of existence here is, of course, smaller. And if the coupling constant is positive, and then in that case also the entropy is smaller, so doesn't hint towards stabilization, I would say. But in the other case, when you have spin-induced scalarization, then the entropy is bigger. Now, doesn't mean that it's stable. It's just some hint, and one really has to investigate. And I mean, since it's all these even functions, one always has to think about, yeah, what's happening up there at these very high multipoles? Is there instability or stability? The last type I just briefly mentioned. Sorry? Manolo, there was a question from you?
No, sorry.
Okay. So the last type, this is just, yeah, that we can also have some nonlinear scalarization. And this means now we also ask that there is no effective mass. So we just take a coupling function higher order in the scalar field. And this was also done by Daniela and her group. And you see down here, instead of 5 to the 2, we now have 4 or 6 up here. And indeed, one also gets such scalarized black holes. The blue part is where no instability has been found in the low multipoles, but yeah, this Japanese paper claims in the high multipoles there is something, but we don't know how relevant this is currently. So the last part of my talk will be now switching over from the black holes to possibly black hole mimickers, something that could be seen sometimes under certain circumstances as a black hole, but could also be very, very different. And these are the exotic compact objects. And let's start with the wormholes. So this is just the sketch of the wormholes. The first, I would say, most relevant in the literature were those from Alice and Bronnikov, and they also appeared basically at the same time, same year. But here we have 2 universes, let's say an upper and a lower universe, and in between we have this throat. So a minimum circumferential radius. We don't want any singularity. We don't want a horizon. So it should be a traversable wormhole that we aim at. And of course, we would like the best, I'm sorry. We would like the best a wormhole that also satisfies all the criteria that we have from Morris and Thorne. But yeah, this is wishful thinking at the moment. But now the first that were constructed in this type of theories were again with the dilaton, because the other scalarization is only much later. And this is, yeah, at the time we were doing dilatonic black holes, and then we realized there are more solutions, and we looked at the papers before, and then we saw in the paper by Jutta, there's also something on solutions. But yeah, no understanding what this is. And then we teamed up with her, and we realized what we have is really wormholes. So this type of theory does allow for wormholes. And the nice thing is one does not need exotic matter in order to construct wormholes, because we get this from this interesting effective energy tensor that allows for that. And we have then studied for this dilatonic theory the domain of existence. And here you see for the static spherically symmetric wormholes the domain of existence. This is the area of the throat now. And here the scalar charge. And you see in here, this is the domain, and the domain has boundaries again. On that boundary, we encounter a funny type of singularity, where all of a sudden some function is making a jump. So we call it a cusp singularity. Down here, we have black holes. So the black holes in that theory also are a boundary. And then there was this boundary on the right. And at first, we didn't understand what was happening there. Our metric functions were behaving strangely in our parametrization. Something was diverging, and it was just clear we couldn't go beyond in this direction. But sometime later, we did what you do in general relativity, right? You change coordinates. You see whether you can make some more sense of something if you use a different set of coordinates. So we used a different set of coordinates, and this clarified what was happening on that side. On that side, our solutions were developing what we call an equator. So we have a throat, but and the throat is a minimal circumference, but then an equator is some maximal. So we have something that we call a multi-throat wormhole. Here we have two throats, and in between we have a maximum equator. So this is quite funny. So we can just go up here with the wormholes with a monothroat, a single throat. It's this whole area. But then from here we can go back down, and then we have wormholes which have two throats and an equator in between. And I just wonder, would the pictures of such a wormhole look different? I don't know if anybody looked at that. And they end here, and right here we would just run into some singularity. So it's a funny new type that we have, and particles, they can have bound states in either universe, but they can also have bound states where they travel from one universe to the other universe. And what you would like to have is also maybe these nice criteria of Morris and Thorne, and which would, for instance, say now the acceleration when you enter the wormhole, when you're at the throat, shouldn't be too big. It should better be on the size of what we have on Earth. And for the dilatonic coupling, we really did the studies, and we found if we insist on that 1G, then the wormhole would be incredibly big. It would be not possible to realize. It would be on the order of 10 to 100 light years. So it wouldn't be anything of help to interstellar travel. And on the other hand, if we would want something smaller, then yeah, this acceleration would explode, and we would have to go through tremendous acceleration, which is also not possible. We extended our calculations then when all that spontaneous scalarization came up to Z coupling functions, and you see basically a very similar picture. This is now with just a phi square coupling, and again, you have here this boundary where we all get the double throat wormholes. This is the black hole boundary, and this is the boundary where we get some curvature, some cusp singularity. Of course, the curvature explodes there also. What is new is that in this case we also can have radial excitations, and just I would say pretty much at the end of the wormholes. I'd just like to explain how we have the single and double throat wormholes, and that they are not completely beautiful wormholes, because when we start calculating and we look at our circumferential radius as a function of the radial coordinate, then coming from large radial coordinates towards the throat here, then we go up again, let's say come to an equator, and then continue integrating and run into a physical curvature singularity. And this is, of course, what we don't like. We really want two nice universes. And so, therefore, because this always happens when we try it, of course, you can never go through all the parameters, but all the parameters we checked, we always ran somewhere into such curvature singularity on the other side, in the other universe. We decided we better kind of cut and paste at the throat or at the equator. And then, we kind of reflect this universe and get the other universe. And this is what you see up here. This is what we actually do. One of the functions that we have here in our metric is perfectly fine, differentiable, and this is not the problem. But the other metric function that we have and the scalar field function is only continuous, but not continuously differentiable. And therefore, we have to put, if we want to have this as a good solution, we have to put some matter right there at the throat or at the equator. And the nice thing is, of course, that we can put ordinary matter. We don't have to have any exotic matter. And we haven't yet for all these many types of coupling functions one can play with. We haven't done any checking of the things of Morris and Thorne of their conditions for travelers. The last points will be now the particle-like solutions and their properties. And just as when we were looking, maybe I go to the next one already. When you're looking at the black holes, we realized there are wormhole solutions also, because we found some more solutions and needed to interpret them. And we were studying now the wormholes. We found some more solutions and we tried to find out what they are. And we realized we have another type of solution, particle-like solutions here. And this means we have a globally regular metric. We have a regular stress energy tensor. However, for the coupling functions we have tried, it was always that the scalar field did diverge at the origin. It may quite be that for some scalar function, this is not going to happen. Yeah? If we find the proper coupling function, maybe this singularity disappears. When we found these, we discussed it also with Jutta and Radu from Avero. And then the Avero group did calculations for this similar type of theories and solutions, but you don't couple to the Gauss-Bonnet invariant, but you look at charged objects and you couple to the Maxwell invariant. And they indeed found a completely regular solution for one of the coupling functions. So it may quite exist also here, but we stopped looking around after a while playing with them. So you have the black holes here. Then there are the wormholes. And in addition, a huge number of particle-like solutions, and there can also be particle-like solutions with a throat and with an equator. So this is just an example how things look like. You make an expansion, and in the expansion you see most things are fine. It's just the scalar field that diverges at the origin. Yeah, it's an expansion at the origin, of course. And this is how these objects look like. These exotic compact objects are sometimes also ultra compact objects, meaning they have light rings, UCOs. And here we have the energy density, and the energy density, depending on parameters, then can be very, very localized, kind of low, like a shell. All the energy density is sitting in a shell, a spherical shell around the origin. And here next to it, you see the photon effective potential. And since it's not a black hole, you have either none or you have two. You have an even number of light rings. And you can just see, depending on the parameters, up here, there's no extremum, and then at some point an inflection point arises, and then we have a maximum and a minimum, an unstable light ring and a stable light ring. And with light rings, they are called UCOs, ultra compact objects. And for these objects, massive particles can be also bound in here in this effective potential, and one has echoes. It's echoes with echoes. So these the effective potential plotted now, let's say for a scalar field. So you look at the Klein-Gordon equation and its effective potential. And let's just look here at this parameter set. Those are just always, these are different parameters that are used. And here for one parameter, we have different multipoles that we consider. Now let's look at L equal to 2 and this parameter. And then we see our potential looks like this. So we have a maximum, a minimum, and then it diverges. As, yeah, when you have a regular object, this is what happens. The effective potential diverges for finite L. And it's not the case, of course, for the black hole. When you have a black hole and now there's such a wave coming in, it's meeting here this potential barrier, and then it's in part reflected and in part it's going to the horizon and yeah, it's gone. But for this exotic compact object, where we have this infinite barrier, we have a wave coming in, it hits this first barrier, and we have partial reflection, and the part goes in. But this part that goes in is now hitting, yeah, the infinite wall. Yeah, it's diverging our potential. And so it's totally reflected. But then, yeah, it's coming back to this potential here, to this mountain. And here we have partial reflection. So a part goes through, this is the first echo, but a part goes back in. And yeah, this part that goes back in is again totally reflected. And it comes back here, and now it's again partially reflected. And so we get basically infinite number of echoes of this incoming scalar wave. Yeah, and I think I'm at the end now, just on time. We have discussed the different types of scalarizations that are popular for this type of theory for the black holes, and we have seen, because of this interesting energy momentum tensor that we have, we get these exotic compact objects, also the wormholes and the particle-like solutions. And yeah, we haven't yet rotated those, neither the wormholes nor the particle-like solutions. And we haven't looked really much at stability, I must say. All these things should still be done, so there's a lot of open questions still in this area. And yeah, thank you.
Thank you very much, Jutta, for this nice talk. Are there any questions? I guess J.O. maybe?
Yes, I do have a question. Thank you, Jutta, for the nice talk. Can you go back to the slides where you show the effective potential for light rays? Yes, this one. So it looks like if you zoom in on the right figure and you focus on the localized case, like the blue and red curves, and near the RC equal to 2, there are some potentials that are multi-valued. Is that right?
Yeah. In this type of coordinate, it's bending back.
Does that make sense?
Gosh, I forgot our arguments. It did make sense. There was no problem at all. But yes, you're and this is a very good observation, but it did not. This is no problem for the solutions for this effective potential. But I just don't recall at the moment our arguments. I can tell you later.
Okay, no problem.
Are there any other questions?
Okay, I have some question.
Yes.
So, seems that so during your presentation, the coupling function f, sometimes chosen as an exponential function or sometimes polynomials, right?
Yes, precisely.
And so qualitatively, how can we say, are there any some property that is more or less independent of the detail form of the coupling function? For example, you mentioned that the entropy compared to the short-shift case is somewhat larger. Is it more or less independent of the coupling function?
No. I mean, one has to really look at the various cases, and I think also the entropy hasn't studied for too many of these coupling functions. When you look at the dilatonic coupling function, then the entropy is always larger. But when you look at polynomials, and with dilatonic is clear. But when you look at polynomials, this is awesome exponential, but of course it's an infinite expansion. And here you do have, for this coupling function and similar coupling functions, you do have positive entropy. But it depends very much also on how these terms in the expansion look like. You seem to need some other self-repulsion, some self-interaction of the scalar field in order to get something that gives you a positive entropy, or then with this positive entropy, when you want to say, okay, when I have positive entropy, then I also observe stability, at least for the low-lying multipoles, then there seems to be some correlation. But what has also been done is not only look at the massless case, and you can also get this behavior. It has to bend inside, so your solution should exist on the branch for smaller masses, so the branches should not bend outside to larger masses, but towards the interior to smaller masses. And there seems to be some correlation, and you can get that also when you take mass, and when you take a potential self-interaction for the scalar field. So in these cases, you can get no instability for the fundamental solution. But I don't think there has always been, in addition, the calculation of the entropy. So I cannot answer this very well, this question.
Okay.
Of course, it's very interesting, and for this case, we have looked at the entropy, and we couldn't get any correlation of the entropy with the stability of the fundamental solution, because the entropy was behaving in a very strange way. So it doesn't seem so straightforward, I think.
Okay, thank you.
Luis?
You were a very clear talk. I had a question regarding the gravitational collapse that you briefly mentioned at the beginning. I think there has been some numerical work on this, but do you know if any analytical work on gravitational collapse in Einstein-scalar-Gauss-Bonnet?
I must admit I don't. I haven't seen anything, but also the numerical work on the collapse I haven't seen that. In particular, I mean, this question, which I would like to know, what is the end state? What is happening there when we would reach a black hole here in this area where we don't have stationary solutions? I haven't seen anything there. And this would be most interesting to me, but I haven't seen any of that, and also not in this analytical range, no.
Okay. Thanks.
Yes, Mr. Rabin.
Yeah, I cannot raise my hand somehow. I have a question. Do you think, Jutta, that there is a cosmological application for this theory? Do you know about cosmological solutions?
There are a lot of studies in this cosmology aspect. I have heard a number of talks where in the early universe the theory has been used. I mean, some claim parts have been ruled out, but yeah, then other coupling functions would work. And for now, where is it? For this one here, it was in fact a cosmological motivation that if you just use the Gauss-Bonnet, then yeah, you might end up in the universe today with some non-vanishing scalar field. And this extra piece was put into the theory in order to just suppress the scalar field today, so that, yeah, you might not run into contradictions with observations.
Okay, thank you.
Any other questions?
Okay, I have some other question. So, I guess the previous page 10 was something that where you showed the horizon size versus the mass, and where seems that yeah, in here. So, can we say that for given mass, the Gauss-Bonnet term black hole horizon is smaller than Schwarzschild?
Yes. Yes,
So
you fix this coupling constant, and you have you look then at a certain mass, and then you're just lower. Yes.
and then the entropy is there is an area law still holds for the Gauss-Bonnet, I guess, right?
No. Gauss-Bonnet, you have to use Wald's entropy, so you cannot do the simple area law, but you get an extra piece from Wald's entropy. So yeah, it's this piece that supports the entropy, which allows it, which makes it bigger. Yes.
So that extra entropy is more or less from some scalar here.
Yeah, it's coming just from the additional piece in the action from the scalar Gauss-Bonnet coupling. Yes.
And in this graph, for given the parameters, there is the minimum mass below which there does not exist black hole, right?
Yes, precisely.
And is it related to your extreme some compact object?
To which?
I mean so.
I mean the exotic compact object.
Right.
Oh, yeah. You always see here when you look at the wormholes. Here you see, yeah, where the limits are from the black holes. So let me see. You have here on both sides something that it goes somewhat beyond, right? So the compact objects reside in a somewhat different regime also, but with the compact objects you can kind of go beyond it. It's not a bound for the compact objects, these exotic ones.
Okay, so to rephrase, the compact object there may be many various kind of compact object, but the question is, if there is any structure. First, I do not know whether there is any structure below that minimal mass of the black hole. And if there is, it should be somehow some compact, new type of compact object, right? So in your study of the exotic compact object, so can you say that, okay, these kind of complex objects are the solutions or objects that are naturally connected below the critical mass? Are there any such solutions that you found numerically?
When you see the bounds here, the bounds of, I mean, there's just this line here, or here, the dotted line, then this is always just in that type of diagram where we have the black holes.
So with a minimum mass, is that right?
The minimum mass is one side, yes.
Okay.
And then it means we can continue there with some solutions, but they go directly here into this curve of singular solutions. You see the boundary is singular, but we could come from other sides. Yeah, we could reach there. So there would be some strange compact objects, exotic compact objects, some wormholes or particle-like solutions sitting there, because for the particle-like solutions, where are they? We have no, they just connect to the wormhole, so it's not particles, so wormholes. It would be wormholes.
Okay, thank you.
Any other questions? Maybe I can ask a question. In the curve space-time, you have like a certain coordinate range for the extremal case, where you can have basically the photon orbits in the Olympic coordinates are spent basically at the same radius coordinates. Did you find something similar for your solutions, or do you know of something fits for those solutions?
Sorry, I did not quite get it. Could you repeat, please?
So when you have the regular Boyer-Lindquist coordinates for the Kerr black hole, and for a certain coordinate, for a certain range, there you have basically photon orbits at the position of the horizon, because basically in the Boyer-Lindquist coordinates they're projected there. Do you know if that something like that also exists for these Einstein-Gauss-Bonnet cases?
I haven't studied it in that much detail. I think if you would ask someone from the Avero group, probably Pedro Cunha, he would be able to answer that immediately, because he has done a lot of orbits and he's the main person doing all these shadow calculations. But we haven't studied these things. And also in our collaboration, when we did the shadows, he did most of the calculations. So he would be the person to ask.
Okay, thank you. Are there any other questions?
I have one more question. It's okay.
Please feel free.
Okay.
Yes.
So I guess you mentioned, you explained about the gravitational wave from the Gauss-Bonnet term. So did you say that from the scalars there can be some dipole radiation?
Yes.
So then and you show the pattern of the gravitational wave. But in the case of dipole, compared to the usual quadrupole, maybe the polarization states would be very different. So can you say, I mean, also first, how strong it will be? I think since it is a dipole, it will be much more stronger than the quadrupole. Am I right?
These are calculations done by the group in Potsdam. And I don't know the details of the calculations, so only what is in their paper, and they don't give, as far as I recall, very detailed explanations on this, but just point out that it's the dipole radiation that shortens then the time until the merger, because I mean it's that which you don't have, and as you can see here in the time scales, it also depends a lot of how strong you make the coupling constant, because a coupling constant big, but not that big yet, doesn't make a big change. So here at 0.7, it's only very small. And then, when you increase further, go more towards the boundary of what we know as possibilities that are still there for this type of black holes. It's it's increasing rapidly with increasing coupling constant. So when the coupling constant is somewhat bigger, there's a lot more radiation of that type. This is how I interpret this.
Okay, thank you.
Okay, are there any other questions? If not, I would suggest to end the official part of the seminar here. Thank you very much for the nice talk, Jutta.
It was a pleasure.